not seminar actually, it's a talk. I am just trying to give you some of the most interesting happenings, achievements that have happened because of quantum mechanics. Now, before I start with quantum mechanics and its achievements, its philosophical ideas, technological achievements, everything included, let me start with something very, very basic. First, we must know what is physics. Now, physics, it is a word which came from Greek language. It has the meaning of science of nature. Now, as you know, nature includes everything around us, beyond us, and even within us. And this definition of physics is really so appropriate and so correct that we realize it today after the development of modern physics and all that. Now, this physics as a discipline subject developed mainly due to the works of Copernicus, Kepler, Galileo, Newton, that all of you know. But of all these, before Newton, it was Galileo who laid the foundation of what is now called classical physics. It was in the early part of 17th century. Galileo came into the scene. He was a professor of mathematics at Pisa, Italy. And by the way, let me tell you that I am very fortunate that a few years back when I visited Italy, I had been to Pisa. And at Pisa, I saw that famous Leaning Tower from which Galileo did his experiments. Daily thousands of tourists, including scientists from all over the world, visit this place. They want to know what Galileo did there. Galileo, what he did there, that is the beginning of physics, He simply tried to show people that whether it is a light object or a heavier object, they fall at the same time on the surface of the earth. You could drop it from the same point. This he proved going up to a story in the Leaning Tower. It is still well preserved. So that was a very important information. That is, he called it gravity. And under gravity, everything falls at the same time interval with same acceleration. This is one of the biggest achievements by Galileo. And also he did a lot of experiments on motions of objects. He used some inclined planes. Now you see that what you know about Newton, he is so famous about his laws of motion. Most of these you hear about laws of motion were already discovered by Galileo. Newton was lucky enough to repeat them again and put them in a very systematic, logical manner, and then he developed them mathematically. But that doesn't mean that Newton is not great. He is really one of the greatest physicists that we have ever. Now, what Newton did, he developed this, and then he also went beyond gravity. He proved that gravity is not simply on near the earth, but it is everywhere throughout the universe, including planets, stars, and that is the law of gravitation, all of you know. Now, also, it's very interesting, I find that Newton was born in the same year that Galileo died, 1642. So, mainly due to Newton, and later on due to Maxwell's, Boltzmann, Faraday's, physics developed very fast. And what we know today about this classical mechanics, heat and thermodynamics, electricity, magnetism, optics, sound, All these together constitute what we call today classical physics. Now, this classical physics ruled the entire physics world up to the end of 19th century. And everybody thought that physics is complete, that you know everything about the laws of physics, laws of nature. The only thing is that you just go on applying this to understand more and more things, how things happen, why things are like that. So this was the situation. But all of you know that by the end of 19th century and just beginning of 20th century, there were some very famous experiments, very sophisticated, powerful experiments, which revealed some new physical phenomena. Just like this, for example, say X-rays, discovery of X-rays, radioactivity, atoms, electrons, all these were known experimentally. But classical physics had no answer how to explain them. No laws of classical physics were enough to explain them what is happening, how to explain this experimental phenomena. That was the situation at the time. And another experimental phenomena, which is well known, that is called black body radiation. That is, black body radiation means the radiation that is emitted by a hot body. It may be metallic and even non-metallic, doesn't matter. You know that when you heat, say for example, a piece of iron, you know, as the temperature increases, the color changes. Red, white, red, yellow, white, then ultimately it becomes bluish. This means from red to blue, that is, energy increases, energy of radiation increases or wavelength decreases. This is called the black body radiation spectrum. Now, what is a black body? I need not go into details. That is not my headache now, because all of you know. But this is one of the most wonderful experiments at that time done. And I think, Chetri, you can show the slide, the black body spectrum.
Okay, sir, I'm sorry.
Yeah, that's correct. You see, you just look at this beautiful experimental curves. This curve shows the energy distribution as a function of wavelength of the radiation emitted by the black body at different temperatures. The color you see, this color is the visible range of electromagnetic spectrum. And beyond this visible spectrum, you have infrared, you have ultraviolet, which are not visible. So entire electromagnetic spectrum is emitted by this black body. Now this is wonderful. Now the question is, how do you explain the distribution of energy given by this curve? You see, it starts from a minimum, reaches a maximum, then again comes down to minimum as the wavelength changes or frequency changes. Now, classical physics was applied. Especially the best formula was proposed by Rayleigh and Jeans. But even the best formula of classical physics could not explain this. You must have seen in the books that if you plot the classical curve, it doesn't come down, it goes up. Okay, it goes up, it doesn't meet anywhere, and it is called ultraviolet catastrophe. But anyway, classical physics was a total failure. And now there is a big dilemma. People were trying to question classical physics. They started thinking, maybe classical physics is not complete, it is inadequate, and you have to introduce some new ideas, some novel ideas, new concept, new mathematics to explain and understand such phenomena. Now you see at the time, Max Planck, you see, he just completed his PhD. And you know, his supervisor asked Max Planck, what are you going to do after this, Planck? His supervisor said, don't pursue physics anymore, leave physics because there's nothing to do in physics. There is no career in physics. But Planck said that, sir, I want to learn something more about physics. Let me stay first. Let me do some work in physics. I don't claim that I will be doing some wonderful work. At least I want to understand the fundamentals of physics a bit more. And we're lucky that Planck insisted to do physics. And you know the outcome. In 1900, Max Planck, he was tackling this problem theoretically. He was a man of theoretical physics. And ultimately, as you know, he came up with a beautiful concept and a formula which could explain this curve beautifully at all temperatures. Now, but the thing is that he had to make a lot of sacrifice. He had to sacrifice the fundamentals of classical physics. How? Because, you see, in classical physics, when energy is transferred from one body to another body, that is when it is emitted or absorbed, it can be emitted or absorbed by any amount. There is no restriction. In a continuous manner, any amount of energy can be emitted, any amount can be absorbed. This was a fundamental concept of classical physics. But Planck said that in this particular black body radiation spectrum, this idea fails. So he simply introduced, he postulated that when electromagnetic radiation is emitted by this black body and absorbed by the experimental photograph or whatever it is done in quanta. That is, electromagnetic radiation emitted by this hit an object as if bullets are firing, bullets are hitting. One bullet, two bullet, like that. Each of this bullet has an energy equal to h into nu. H is the Planck's constant, nu is the frequency of radiation emitted. And it may be 1 times h nu or 2 times h nu or 3 times h nu. It depends on the temperature of the black body. Now, this was a novel idea. Once he introduced this concept, he could derive a formula successfully, and that explained this curve. That was the, and we now say that that was the birth of quantum mechanics, because the word quantum was used by Planck at that time. This small amount of energy h nu, which you nowadays call photon, but remember, photon name came only in 1926. Before that, it was only some quantum of energy. So this quantum of energy h nu and the Planck's constant h, how he introduced this, that you can read from any fundamental, any elementary quantum mechanics books. I am not going into this. It's a very simple derivation. Now, you see, so that was the beginning of quantum. We say that is the birth, and the exact birth of quantum mechanics recorded and accepted by everybody is 14th December 1900. Why? Because it was on that day that Planck gave a seminar on this work in the physics department of University of Berlin, where he was working, before the audience. But you'll be surprised to know that when he presented this idea and this formula, the audience, which included many well-known physicists, they could not understand. They simply laughed. You know, laughed means not openly, but simply they just did not show any interest. They thought that, what is this nonsense? Is it some mathematical manipulation? What is this? No, how can it be? It is totally wrong. It doesn't agree with classical ideas. So people were just like that. And, you know, Planck started his seminar with a good hope, lot of hope, but at the end of the seminar, he felt very dejected, very dejected. And when he went home, his son simply asked him, "Father, you must have been praised a lot. People must be giving a lot of praise to you. Their, very appreciations and all that, honor and all that." But when he found that father is not responding, he's not looking very happy, and what happened? Then Planck told his son, "Son, my dear son, you will see that these people today, they don't understand what I am telling. I am telling a truth. And you will see that a time will come when they will have to accept it, and they will have to accept that I am as great as Newton." That is what he told secretly to his son. And you see how true he is. He was so confident of his work. Now, so that is Planck. And let me tell you, Planck, because my dear students and also my dear teacher colleagues, let me tell you that nobody can understand and appreciate quantum mechanics unless they go to the history of development of quantum mechanics and try to know those brilliant young physicists, a good number of them, who contributed towards this development, how they used to work, what was their philosophy of life and everything. This will inspire any serious student of physics. Unless we do that, nobody can understand the beauty of quantum mechanics, the worth of quantum mechanics. Quantum mechanics is so difficult, we say, whether conceptually and also mathematically. It is difficult because we don't know how to love it. You see, I still remember when I first encountered quantum mechanics, it was love at first sight. As I went deeper and deeper, I was so fascinated by these ideas, and I started reading whatever I got on quantum mechanics. But anyway, I'm not going to that. But it is an advice to all those who are interested in quantum mechanics. Please go deeper and deeper into its development. Deeper and deeper. Simply don't read it superficially. You have to change your mindset. You must have a clear mind, clear thinking, and dedication, perseverance. These are the things are needed to understand quantum mechanics. And once you understand this, your mind will be totally different. Your thinking process will be totally different. And you will see that you are in a magical, mysterious, mystical, and metaphysical world. These are I say quantum mechanics is mysterious, magical, mystical, and also metaphysical. What else you need? No other field of science can claim all these qualifications. Now, you see, okay, that was 1900. Let me come now quickly. Then coming back, 1900 it was proposed, but it was ignored for 5 years. Then it was 1905. 1905, the most important year in the development of physics, because in that year, none other than the greatest Albert Einstein came into the scene. He appeared on the platform of physics. I am not going into the details. So it was in 1905 when Planck was writing 3 revolutionary research papers in the same year and published in the same year. Now, one of these papers was on photoelectric effect. And you know that till then, we had a lot of experimental observations on photoelectric effect, but no theory to explain these experimental observations. Then Einstein was thinking seriously about this problem. Then he came to the conclusion that classical ideas will not help. And immediately he studied Planck's concept. And he applied this concept of particle character of light to explain this photoelectric effect. And it is a single formula As you know, h nu equal to half mv square plus work function w. Very simple formula. And that explained all the experimental observations on photoelectric. That is, he used the concept that when light falls on a metallic surface, it is not hitting the surface as a wave, but as a stream of particles, as a stream of bullets, each bullet or particle having the energy h nu. So it becomes a particle-particle collision between a photon and an electron on the surface of the metal. Electrons are emitted due to particle-particle collision. This simple picture explained everything about the photoelectric effect. And by the way, you know that this was only a 1.5 page paper for which he got Nobel Prize in Physics. See, he got Nobel Prize in Physics only for photoelectric effect, not for theory of relativity. But he is more known, more famous for theory of relativity. That's a very interesting point. Anyway, so once Einstein proved this, the people were trying to look back at Planck's hypothesis. They are trying to have some faith on Planck's hypothesis. Then I'm quickly coming to, next came Niels Bohr. You know, till then, we did not have any theory for the atom, how to look at the atom, how the electrons are moving around the nucleus or like that, whatever it is. Rutherford already, he already gave us the model, nuclear model of the atom, but even Rutherford failed how to explain the stability of the atom. So it was Niels Bohr, his student, that for the first time gave us the most successful model of the atom, hydrogen atom, by using 3 postulates. And in these 3 postulates, if you remember, that he uses mixture of classical physics and quantum ideas used by Max Planck. So his theory for the atom, the model for the atom, is not purely quantum. It is semi-classical and semi-quantum. Only thing is that he uses the concept of h nu. That when the energy levels and electron makes a transition from one energy level to another, the energy is emitted in terms of photons or h nu. So this was the idea. And also he used the quantization of angular momentum of the electron, all these things. So you know all these things. So what I said that it was Niels Bohr who first successfully applied this new Planck's concept to have the first model of an atom. It's okay. So then I'm coming to 1923. In 1923, another famous experiment, Compton scattering. This is a scattering of X-rays by electrons. There also, Compton proved that X-rays consist of particles. X-rays is a form of electromagnetic radiation, but here also he proved that X-rays, when it's scattered by electron, they behave like a stream of particles. So starting from 1900, then coming to 1923, you see that electromagnetic radiation, like light, show particle character. They behave like, you say, particles. Now the question is, does light also behave as a wave? The answer is yes. Because already in classical physics, long before Planck's hypothesis, it was known that light also shows interference effect, diffraction effect, polarization. All these phenomena you can explain only by using the concept of wave theory of light that you already know. So those are also correct. Those are also experiments. And these are also experiments, photoelectric effect or Compton scattering. These are also experiments. So you now see that there are 2 sets of experiments. For one set of experiments, you have to assume light as a wave. For another set of experiments, you have to assume light as particles. So this introduced a lot of confusion among the physicists. And let me tell you one thing, that when this was the situation, you must have heard about Bragg's law. Bragg was teaching optics in the University of Sydney at that time. And he was so confused what to teach the students. Is light a wave or a particle? So there's a famous sentence. I will just read it to you. You see, when this was the situation, he told that God runs electromagnetics on Monday, Wednesday, and Friday by the wave theory. And the devil runs it by the quantum theory, photons, on Tuesday, Thursday, and Saturday. So he used to teach like that. So this shows that they were in dilemma. What is light actually? Is it a particle or a wave? Okay, that I shall come to later. Now come to 1924. This was the situation with light. Now I am coming to material particle. 1924, as you know, Louis de Broglie, he first proposed theoretically that not only light, not only electromagnetic radiation, but even a material particle like electron or atom, whatever it is, microscopic particle, can have wave properties. And as you know, that these wave properties were proposed theoretically in 1924. And that was his PhD topic, University of Paris. And do you know, when this thesis was sent to examiners by the university, all the examiners sent it back saying that this is a madman, this is all madness. How can a particle can behave like a wave? And university was at a loss what to do. And at the time, they simply sent a copy of the thesis to Einstein for his comment. And when Einstein went through it, he was so fascinated. He said that this is a brilliant idea. And he wrote back to the university saying that it is a brilliant idea and this young man must be awarded a PhD degree without any doubt, without any confusion. And that is the history behind it. Now, in the meantime, when this hypothesis was produced in 1925, a lot of discussion was there, a lot of seminars were there on this. And in one of this seminar, it was Schrodinger in the University of Zurich who presented a seminar on this wave particle hypothesis of particle like electron. Now, it was in that seminar that Professor Peter Debye raised the question that if there is a wave with the particle, then one must have the equation for this wave. Now, this question, inspired Schrodinger to think about this equation. And as you know, that when he was inspired by this question, he tried to develop an equation for the wave associated with the particle. Now, that is the famous Schrodinger equation. I'll come to that. Now, in the meantime, in 1927, during 1927, de Broglie's wave particle hypothesis was experimentally verified. Dr. Chetri, can you show that slide, please? Yeah, you see, this is just shows that what happens to electrons and the ordinary bullets. You see that there are two slits. If you send a stream of bullets in the upper figure, you see you don't get any interference pattern. It's simply two peaks like that. And the average is this, that is shown. Only two spots will appear on the screen, okay? But if you consider electrons passing through the slits, but remember, the size of the slit is not ordinary size. It must be of the size of angstrom, because electron wavelength is very, very small, of the order of angstrom. So the size of the slit also must be of that order. As you know, that wave properties can be exhibited only when the size of the object interacting with the obstacle are almost the same order. Now you see Actually, this this only picture, but actually these slides are nothing but the crystals, crystal spacing. Now, you see that when electrons pass through these two slits, you get a beautiful interference pattern shown by wave, any wave. Now, this shows the difference between ordinary particles, classical particles, and the electrons. Next slide, please. You see, this is another photograph. See the patterns, fringe patterns, we call it fringe patterns. It is only interference pattern. So this ultimately proved that de Broglie's particle wave hypothesis, that electrons, particles can have wave properties, verified, justified, proved. So now everything is clear. After this, people understood that not only radiation, but even material particles have dual properties, particles as well as wave. Wonderful symmetry. And this is expected. Whatever must be true for radiation or energy must be true for mass. You know from Einstein's equation, E equal to mc squared. Energy is converted into mass, mass can be converted. Actually, in this universe, let me tell you, only two things are there, energy and mass, that's all. And their interactions, nothing else. So there should be a symmetry. Whatever is true for mass should also be true for energy. So this was vindicated by these discoveries. Now, you say, I am now coming back to this, coming to the Schrodinger equation. Now, before that, please, can you show me the next slide? Next slide, okay. Sorry, there's a phone call. Now, you see, yeah, now I'm coming to the fundamental equations starting from classical physics. You see, look at this, because you must know the difference between this classical equation, quantum equation. This is the famous Newton's second law of motion. What does it say? Remember, there are three laws of motion. But only this is the most important, because other two laws are simply corollaries of this. You can prove it. Now, you see, this is the fundamental equation of motion. Look at this. See, this equation says that what will happen to the particle if a force F acts on it, a particle of mass m. On the right, you have acceleration. Now, this is a second order differential equation. You can solve it exactly once you know the force acting on the particle. So once you know how to solve it exactly, it can be done. Then you know the trajectory of the particle r as a function of time. So at any time, we know where the particle is. At every moment, we know where the particle is. This means we know the exact trajectory of the particle. This is called Newtonian mechanics. There is no indeterminacy, there is no uncertainty. We know the motion exactly at every moment. This is the basic of classical physics, classical mechanics. Next slide, please. Now, you see, before Schrodinger, historically, that's why I told you one should know the history of quantum. Before Schrodinger, in 1925, it was another young, brilliant physicist, Werner Heisenberg, who came up with a very, very revolutionary equation. It is called the matrix mechanics, foundation of matrix mechanics. You see, this is the well-known Heisenberg equation of motion. But remember here, the A, dA, dt, this A is not an ordinary variable, but it is a matrix operator. It represents a physical property. And H is the Hamiltonian of the system. And this bracket AH, it is quantum bracket. You call it quantum bracket. It's AH minus HA, and most of you must be knowing. Now here, you see that Heisenberg developed this equation. And in this equation, there is no question of trajectory. You don't have to calculate any trajectory. It is meaningless. What you want to know is how to calculate the time development of a physical properties of a system if you know the Hamiltonian of the system. So it simply gives a prescription for calculating any physical property as a function of time. Now you see, let me tell you, it's a very interesting incident is there. Heisenberg, when he was very young, hardly 23 or 24-year-old at the time, he was thinking about this atomic problem, how to understand the atom. Because Bohr's atomic model was not the correct, finally correct, it was simply an approximate model. So he was thinking of how to explain the hydrogen atom spectra in some other way, which will be without any limitations, without any approximations. And he was thinking very, very seriously, very, very seriously. And you know, at one time he almost fell ill. He was suffering from hay fever. You know, he was working so fast, so vigorously. Then Pauli, as you know, famous Pauli advised him that, young man, you don't exert yourself so much. Your health is going down. Why don't you go for some vacation, take rest? And accordingly, he went to a famous island. It is called Heligo Island, and to spend some time there. But as you know, although he was not well, he was still working and working. Why I should not get the equation? And working the whole days without any sleep, he ultimately got his formula, this equation. And see his reaction when he got this equation. I'll just, in his own words, he writes, Heisenberg writes, I quote, "It was about 3 o'clock at night when the final result of the calculation lay before me. At first, I was deeply shaken. I was so excited that I could not think of sleep. So I left the house and waited for the sunrise on the top of a rock." See how excited he was. And next day, he sent a telegram to Pauli. He was called back and presented his paper. This was the history, you know, about this development of matrix mechanics. He's a wonderful, very brilliant young man. Now, just about 6 months later, Schrodinger developed another equation. Please, next slide. Now, this is the more familiar Schrodinger equation. All of you must be familiar with. It was developed between 1925, latter part of 1925 and earlier part. You see, this is a wave equation. Why? Because it has your first order time derivative, you have space derivative del square. So, you know, this structure of a wave equation, you must have derivatives with respect to time, with respect to space. And this psi, the well-known function, it is called the Schrodinger wave function. Now look at this equation. It doesn't look like a wave equation in classical physics. First thing is that Planck's constant is appearing, h slash is h by 2 pi. Then also you see that mass of the particle is appearing, m. In nowhere in classical physics, a wave equation contains mass. Because a particle of mass m cannot have wave properties in classical physics. But this is quantum. He is combining the wave properties and particle properties together using lambda equal to h by p, that Planck's hypothesis, and also the Planck's hypothesis E equal to h, and also de Broglie's h by p. So both were combined together to derive this equation. Now look at this. This is the basic equation we say in in quantum mechanics. Actually, it is non-relativistic quantum mechanics. I'll come to this. It is non-relativistic quantum mechanics. Now here you say, you should know the difference between Newton's equation and this equation. In Newton equations, force the force plays the prominent role. But here force is missing. In place of force, you have the potential V appearing. This is one of the most important difference between classical and quantum mechanics. In quantum mechanics, nowhere in the dynamics force appears. It is the potential. This is the most important point to note. Now, not only that, this is the equation. When you solve it, suppose you know the potential in which the particle is moving, you solve it, then you find out the wave function psi RT. Now you know the wave function psi RT, but what does it give you? It doesn't give you the trajectory. It is not a function of, it is not R function of t as in Newton's equation. It is a wave function. So here, trajectory is not given directly. That was a big problem at that time. And later on, of course, you know that what is the physical significance of psi? It was given by Max Born in 1926. And we now know that this psi is associated with the probability of finding the position of a particle at a given time. Actually, it is psi modulus square you have to take, because psi itself is a complex quantity, because the differential equation contains the imaginary quantity. So psi itself is a complex quantity, and a complex quantity cannot give you probability or a position like that. So one can form a real quantity psi modulus square, and this has been interpreted as the probability of finding the particle at a given position at a given time. So this you already know. Now, once you know this psi, all physical properties can be calculated. In quantum mechanics, remember, we are not bothered about what is the trajectory of the particle, whether it is a circle, ellipse, or straight line. We are not bothered about it. We are simply bothered about what are the relevant physical properties we can talk about. What are these properties and how to calculate them? That is the essence of quantum mechanics. So this is what I say. Now, next slide, please. Yes. Now, 1928. You see, Dirac equation. Now, Dirac equation, it was a new equation. You might ask why Dirac proposed this equation, why he developed this equation. Now, you see, as I told you, Schrodinger equation was non-relativistic. Einstein's special theory of relativity was not combined. So Dirac wanted to have an equation where relativity will be taken into account. And then he, after a lot of calculation, he was one of the most brilliant mathematician and physicist, theoretical physicist. He arrived at this famous Dirac equation. Now you see, this is a very wonderful equation, and mathematically a bit looks to be complicated also. It is not a simple equation like the Schrodinger equation. If you look carefully, you see there this vector alpha, you see in that equation, then a quantity beta, alpha, beta. New quantities are coming. Now, this alpha, those who have understood or those who have read this, I am not going into details. You know, this psi, the solution of this is not a single function, but it has four components: psi 1, psi 2, psi 3, psi 4. Why? Because the alpha and beta which Dirac introduced, they are not ordinary numbers, but they are matrices. Alpha is a 4x4 matrix. There are 3 alpha matrices, alpha 1, 2, 3. That is why it is called a vector matrix, and beta is a scalar matrix. So totally there are 4 4x4 matrices, 4 4x4 matrices appearing in Dirac equation. So now you can easily imagine how difficult it will be to apply this equation to physical problems. But it has been done with great success. Now, let me tell you one thing, that every theoretical physicist say that the most brilliant equation of quantum mechanics is Dirac equation. It explains everything about the electron. It explains not only the atom, hydrogen atom, energy spectrum, everything, but it gives almost all the properties of the electron. Let me give you why. Let me tell you why. You see, if you look at Schrodinger equation or non-relativistic equation, we cannot understand why electrons would have an spin angular momentum. You know what is spin angular momentum. Now, let me just tell you briefly, because concept of spin is somewhat least understood by not only students, but also by many teachers I have seen. What you should understand is that though we say spin is a angular momentum, it is not like classical angular momentum. It is a purely quantum concept. And orbital angular momentum, which is classical, it may be zero, it may take any value, it may change with time, it may change with motion. But spin is something which is inherent, that is intrinsic. It is always there. Whether the electron is at rest or in motion, it is a definite value of spin or spin angular momentum. That is a great mystery discovered by experiment, displayed by experiment, the famous Stern-Gerlach experiment, anomalous Zeeman effect. All these point out this existence of spin, right? Now, but nobody could understand theoretically what is this spin, how to calculate it, where from it comes. Nobody. And physics is never satisfied without a theoretical explanation. It was Dirac for the first time who proved, starting from his equation, his Hamiltonian, that an electron must have not only orbital angular momentum, but also a spin angular momentum. And he calculated the values, it can be done, which value half h slash, exact value, which is found experimentally. So this was the first time that the concept of spin of electron followed naturally from a theory, one of the greatest achievement of Dirac. Another achievement of this equation is that in order to explain the physical properties of the wave function psi, Dirac had to propose, he proved it, that there is a new type of vacuum in quantum mechanics. It is called quantum vacuum. I'm not going into the details, but to introduce this quantum vacuum, he justified it. What is this? And that concept of quantum vacuum is still valid today. Remember, vacuum has two meanings in classical vacuum and quantum vacuum. When I say classical vacuum, there the meaning is that vacuum is where nothing exists. Vacuum is where nothing exists. This is classical vacuum. In quantum vacuum means we say that quantum vacuum is where nothing is observed. Nothing can be observed. Say nothing can be observed and nothing exists have a lot of difference in meaning. Now, using this concept, Dirac proved that if there is an electron, there must be an anti-electron, antiparticle. Anti-electron means mass is the same, spin is the same, but charge will be positive. Electron charge negative, anti-electron will be positive charge, same magnitude. This he proposed to save his equation. And this was proposed in 1930. And you'll be surprised that just 2 years later, this anti-electron was discovered experimentally, which we call positron today, positron. So that was Dirac. Not only that, this Dirac equation gave foundation to another development in quantum mechanics, the quantum field theory. Once he introduced this concept of vacuum, it laid the foundation for quantum field theory, right? Now, Chetri, can you so now you see, after this, I will come to the basic ideas of quantum mechanics. Let me first complete this. What is the quantum mechanics now as of today? This is called method of second quantization or field quantization. This is the foundation of quantum field theory. Here you see, very interesting. H is the Hamiltonian. It looks a bit complicated, those who are not familiar with advanced quantum mechanics. But what I want to point out, this is the Hamiltonian operator, which gives a total energy. Now here, This we need because if you see the Schrodinger equation, it describes the motion of a single particle. Remember. But suppose you have a situation like this. Say you are studying condensed matter physics, where suppose you are studying conductivity. In conductivity, billions of electrons take part. In ferromagnetism, billions of electrons take part. Everywhere, in superconductivity, everywhere. Now, so we must have a theory which can describe the motion of a large number of identical particles simultaneously and calculate the energy and all that. This was the toughest problem, but this has been achieved. Mathematical techniques have been achieved. This is called the method of second quantization. And here you see no other operators are necessary, only two operators to introduce. It is called creation operator and annihilation operator. A.K. Dagger, that's Hermitian conjugate. It is an operator. It is called creation operator. K means momentum. That is, it can act on a state, quantum state, and create a particle with momentum K. And AK is called the annihilation operator, which acting on a state destroys a particle in that state. Beautiful. And just in terms of these two operators, you can write the Hamiltonian operator. The first term is the single particle operator. The second term here is the particle-particle interaction, two-particle interaction. So this Hamiltonian is the fundamental for studying the properties of many particle system. Next slide, please. Now you see, this I deliberately wanted to show you. You see, when quantum field theory was developed, things changed very rapidly in the development of quantum mechanics. R.P. Feynman, all of you know. Then, you see, in the meantime, we knew that even proton, neutron, they are not fundamental particles. Proton consists of quarks, neutron consists of quarks, mesons consist of quarks. By the way, this concept of quarks were introduced to explain the strong interaction force. Now, remember, we have a very wrong concept. The strong nuclear interaction or the strong nuclear force, it exists within a proton or a neutron or within any hadron. The force between proton and neutron or neutron and neutron, that is not due to quarks. That is due to pi mesons. And it is only a residual interactions out of quarks. That I will tell you later on. But in the meantime, what I say that it was already known, proton, neutron, they are not fundamental particles. There are quarks within them. These quarks are bound together by exchange of gluons. Gluons are like photons in electromagnetic interaction. Now you see, Feynman, he developed a very powerful techniques called Findman Diagrams. Once you draw the diagrams for a particular physical interaction, you can solve it using the mathematical formulations. It's very easy. Now, the first diagram shows you the interpretation of how we look at electron-electron interaction in quantum field theory. Here you see, we are not bringing any Coulomb force. No concept of force. Electron, when two electrons come closer at 1 and 2, you see, one of the electron can emit a photon, the other electron absorb it. And this emission and absorption of photons take place. Now you might ask, sir, where is the Coulomb force? Now, according to quantum field theory, electromagnetic field consists of photons. Electromagnetic field consists of photons only. It is exchange of photons by which electromagnetic interaction takes place. This is the new idea of quantum field theory. There is no concept of force coming into. So it is simply exchanging of photons by which interaction happens between two charged particles. Two electrons, you see, then emitting, absorbing, and then the two electrons are scattered with different momentum. This is a momentum conservation, K1 plus K2, K3. It's very simple. This is electromagnetic interaction. Next, I'm coming to proton-neutron strong interaction. Here, you see again, according to quantum field theory, it is exchange of pi zero. There are three pi mesons, pi zero, pi plus minus, but I am taking only one example. Proton and neutron, it is exchanged, the interaction takes place through the exchange of pi zero, and it is also one type of strong interaction. Now, please come to next slide. Now here, this is a bit, this is called chromodynamics. Now we are coming to chromodynamics. When you see, you must be hearing about quantum electrodynamics, quantum chromodynamics. These are very exotic names. These are all quantum field theory. Now, quantum electrodynamics is simply, it studies interaction of electromagnetic radiation with matter. Here only electromagnetic interactions are involved. In chromodynamics, we have strong interaction, nuclear strong interactions. Chromo means color. So here what happens, this existence of quarks are proposed. They have been experimentally observed also. But remember that I tell you the green, blue, green, these are quark. Quarks comes in three colors: blue, green, and red. And all these colors exist within a proton as well as within a neutron. And when you combine these three colors, it becomes colorless, white. That is why proton has no color, neutron has no color charge. But you might ask, what is this color? Is it the color we understand? No. Remember, this is just a name. This color is simply a degree of freedom. Because here, electric charge is not involved. It is a new type of charge involved in this interaction, and we call it the color charge. And this color charge is carried by what is called gluon. In electromagnetics, the electric charge interaction is carried through photons. Here, color charge through gluons. So gluons also can carry color. You see, green and blue are interacting, quarks, blue quarks and green quarks, they can interact through exchange of gluons and again become blue. Color may change. Color may change. If color can change, that color is carried by gluon. So this is strong interaction between a green quark and blue quark that I have shown you very soon. So I think this is one of the most wonderful picture which we use using the concept of Findman diagrams to illustrate the matter. Please, next slide. Now, you see, those who are doing BSc physics or even, I don't know, maybe BSc physics, you are all familiar with beta decay phenomenon, nuclear physics. A neutron decaying into proton and electron and antineutrino. We simply call it beta decay. Remember, in quantum chromodynamics and quantum field theory, we call it an example of weak interactions. There are 4 fundamental interactions. And in quantum mechanics, gravity does not come into. All other 3 interactions, electromagnetic, strong nuclear, and weak interactions come into play. Now, you see, this is the modern view of chromodynamics. What is this beta decay? How it happens? Nobody could understand before this chromodynamics. You see, neutron. A neutron is not a fundamental particle. It consists of 2 down. Let me tell you, there are 6 types of quarks. 6 types of quarks: up, down, top, bottom, charm, and strange. These are called flavors. So neutron consists of 2 down quark and 1 up quark. Proton, 2 up, 1 down. So what happens when proton and when a neutron, neutron, you see, neutron going to proton. How it goes to proton like this? One of the down quark becomes an up quark. As you see, it becomes an up quark by emission of a W minus boson. This is responsible for weak interactions. weak interaction. And this again disappears, giving rise to two particles, one electron and this neutrino. Now you see that this is called anti-neutrino. I have shown the arrow coming backward. It is going forward, it's time axis. So electron is a particle, it goes forward in time, but neutrino is an antiparticle, it goes backward in time. This is the Findman interpretation of antiparticle. So it is Findman diagram, so we have to reverse the arrow to show that it is antiparticle. Now this, what I want to tell you, that in weak interactions, the three particles are involved in the exchange of interaction. The Z particle and to this W particles. So this you already know. So everywhere in quantum field theory, the interaction takes place through certain bosons. And in electromagnetics, you know, which is photons, and in strong interactions, gluons, but here it is Z and W bosons. So this now almost gives us what is called the complete standard model of particles, what is known as standard model of particles. And now we have a very almost a complete knowledge of particles, their interactions. So this is one of the greatest achievements of quantum theory. Now with this, after this, I would like to come back to some of the most important concepts of quantum mechanics. Dr. Chetri, how much time I can take now?
So you can take, sir, unlimited time, sir. We are just listening you, sir.
No, I think people are not bored.
No, they are definitely not bored, sir. I can take guarantee of that.
So I will just for some time more, because some of the concept I have not come to, and then the question hour will come.
Okay, sir.
Now you see why quantum mechanics is magical, mysterious, metaphysical. Let me come to the philosophical aspect. It's very interesting. First, we have seen that what is an electron? Is it a wave or a particle? This question comes to everybody's mind, whether you are a student or a teacher. This question came to the minds of Niels Bohr, Einstein, and all those great physicists. And you will be surprised to know that all the brilliant physicists, Schrodinger, Niels Bohr, Heisenberg, Pauli, all these, they had a seminar in Copenhagen just to know what is an electron. How do you define an electron? Now I will just give you the ultimate conclusion. The conclusion was that the word particle, the word wave, these are classical language, classical words. And in quantum mechanics, these words do not have the same meaning as we have in classical mechanics. So don't call electron a wave or a particle. Leave it. Don't call it by any other name. Simply say an electron is an electron. It is a quantum entity. It is a quantum object, a fundamental quantum object, which sometimes can behave as a wave and sometimes as a particle. That's all. The next question comes, when I will see it as a wave? Well, before you try to observe it, you cannot come to any conclusion whether it is a wave or a particle. It may be either. So you do an experiment. Suppose you want to see whether it is a particle. So you have to correspondingly devise an experiment which will detect the particle property. An electron will appear as a particle. Like a bullet hitting a point, bullet hitting a photograph, it will appear like that. So it depends on the type of experiment They have to design to observe the electron. Next, suppose I want to know, does it also behave like a wave? Then you set up an experiment like interference, reflection, whatever. Then send a beam of electrons. And there you see interference patterns. So their electron is behaving like wave. So it depends on the experiment by which you look at it. If it is a particle, then corresponding experiment will be like that and this. So it raises a fundamental question of philosophy. What is reality? What is actually electron? What is its real character? In quantum mechanics, we say that reality has no objective meaning. It has no unique absolute meaning. It depends on the observer. Reality is determined by the observer. Reality may be different for different observers. Reality regarding an object. What is an object? Its reality depends on who is the observer and how he or she is observing it. This is one of the very important philosophy which have been accepted by each and everybody and which has been borrowed by philosophy also, literature, philosophy it has found. Now, this introduces a very important concept in our way of thinking, that is reality. Reality about an object, how it will look like, how it. So now we say that reality means like this: object plus observer plus observation. So reality depends on these three together. They must interact. Then reality comes out. The knowledge comes out. Knowledge. We mean reality means knowledge, what you know about the object. For that, object must be there, the observer must be there, and the act of observation. Only then the reality will come out. Now, let me just, I always give you some examples like this. Even in day-to-day life, people might think that it is only in quantum mechanics. Even in our day-to-day life, this quantum concept is very much applicable. I always jokingly tell my students and teachers, I mean, whenever I talk, you see, suppose in a college, there are young generation, young boys and girls, you know, every girl wants to fall in love with a handsome boy, and a boy with a beautiful girl. This is there. Now the question is, what is this beauty? Beauty lies in the beholder's eye. Can you have a unique, beautiful person? Everybody will call it is the most beautiful? No. If there is only one most beautiful or handsome boy and others are not beautiful, then what will happen to the girls? And reverse is the case. If you say that there's only one beautiful girl in the college, what will happen to the boys? It will be desperate. So God has created quantum mechanics to tell you that all these concepts, ugliness, beauty, they lie in you. How you look at it, how you think about it, how you interpret it. This is the essence of quantum philosophy, one of the most important. Right? Secondly, nothing is exactly determined. There is an element of uncertainty. I did not tell you about the famous uncertainty principle. Everybody knows about that, Heisenberg's uncertainty principle. That is, if you want to know the position and momentum simultaneously of a particle, it is not possible. There is always an element of error, element of uncertainty of the order of Planck's constant. This is a limiting case. So now, again, this introduces a philosophy that nothing is determined. Everything is probable. Probability is coming. Probability. See, you cannot predict that a particle will be here at this moment. In classical mechanics, you can predict. Even if I know everything, suppose I know the initial parameters of a particle at this moment, then using Newton's equations, I can predict what will happen at any time later on. Future is determined. Future is determined. But quantum mechanics say, no, you do not know anything what is going to happen even next second, next minute. This is another philosophical aspect which is quite interesting. You see, because there is always an element of uncertainty, you can also only say that which is most probable, which is least probable, but you cannot say this is going to happen. Sometimes I tell my students jokingly in the class, when they ask me, are you coming tomorrow for the class? I said, I cannot say today. If tomorrow happens, I will come. Because you don't know what is going to happen next moment. Nobody knows. So how can you with certainty say, yes, tomorrow I am coming? How can you say? So these are some of the ideas which have been given by the quantum mechanics. So then you see, another aspect I'm telling you, what is called quantum entanglement. Quantum entanglement, it's the latest concept and a lot of experiments have been done now, verified. What does it mean? You see, there are particles like electrons. Electrons have spin. Now, it can be shown that suppose you produce a pair of electrons simultaneously, then as you know that they have spin, and because of Pauli's exclusion principle, if one spin is up, the other must be spin down. Because according to Pauli's exclusion principle, you know, no two electrons can have the same state, same quantum state at the same place. So up and down. So they are produced like that. Now, what is important or what is said by quantum mechanics is that there's a strong correlation. That is, this up and down remains for all the time. Even if you separate the two electrons, that is, you have produced a pair of electrons which spin up and spin down, then even if you take them far, far away, both are separated, this property is preserved, correlated, it remains. Even if the distance is such that even light cannot reach from one point to another, this property remains. Now, this aspect has been called as quantum entanglement. It is permanently, the two electrons are permanently entangled, correlated. And such correlations or entanglement have been done by a lot of experiments recently. I have already gone through, not only in case of electrons, but also in case of photons. This entanglement is a reality. Now, what does it have? It has a lot of implications. It has one very important technological implications. That is what you call quantum teleportation. This is a new concept coming up. Quantum teleportation means, suppose that two electrons are separated by large distance, then if you disturb one of the electron by giving some message, that other electron is also disturbed, because if you are disturbing the spin of that spin is also disturbed. So the message is carried, but it is not materially. It happens like that. It happens. It is like as if sort of telepathy. Now, so this raises a possibility that if you have a message given to the electron, at a far distance, that electron will communicate the same message. Now, this is the fundamental idea behind quantum teleportation or quantum computation. Quantum computation. You can send a lot of, these are all technical terms. I cannot go into these qubits and all that. Now, people are doing, and it is already in the experimental laboratory stage. They have shown the promise of quantum computation, of course, in the laboratory, but still it will take some time. And if such a computer comes into being in our lifetime, it will have some million times more powerful than the best computer we have today. So that is one of the very interesting. Now, you see, this telepathy, what you call this quantum entanglement, in just yesterday, I read one news, some of you must have read it. You see, this is called a twin effect. Twin effect, you have seen in some movies also. If there are twin brothers, if one brother is not feeling well, the other also feels that he is not feeling well. This you have seen in the movie. Now, latest, I have there was a news when CBSE exams were announced. The twin sisters. There are twin sisters, and exactly alike. It was in the news channel, and that their marks in the CBSE are exactly same. Every subject. How it could be. So anyway, that is also a mystery. But what I wanted to tell you is that quantum mechanics, as of now, is very, very exciting. It is still progressing. It is still developing faster. There seems to be no end. And I am talking about this micro world. But remember that this concept of quantum mechanics are equally valid in stars, planets, galaxies, entire universe. Entire universe. You cannot explain why sun is radiating so much power daily. How? What is the mechanism? Sun is radiating energy through the interaction. It is called weak interaction. This weak interaction is responsible for nuclear fusion. That anybody can understand. I mean, you can just read in literature or maybe in some Google articles. So even sun, energy production, classical physics fails. You cannot explain. It is through only weak interactions. Now, you must have heard about the white dwarfs. White dwarfs. It is one of the very exotic object in the space. It is some of the stars, they reach this white dwarf stage. I am not going into details, but nobody could understand why white dwarf is stable. Why it doesn't collapse under gravity? Why it doesn't collapse under gravity? And now we know that white dwarf is stable because of electrons. Because when proton, neutron, these protons and neutrons are not sufficient. These electrons play a very important role there. That is, electron spins. No two electrons can come close together. It is called spin degeneracy. So there will be billions of electrons. So when the gravity acts towards the center, these electrons oppose. They act like a repulsive force, so that there's some sort of balancing act, and the white dwarf is stable. Similarly, neutron star, it is due to neutron spins. So all these things you already know. So what I want to tell you that not only these small particles, small systems, micro world, but even in macro world, in the bigger universe, quantum mechanics operates. Now, all of you know about the Big Bang theory of the universe, that you already know that universe had a beginning. But do you know this beginning, what happened at that moment? Only quantum mechanics now understands. It has given us a very convincing answer. I'll just give you one thing. According to this quantum theory, latest quantum theory, this Big Bang, when nothing was there, no form, nothing existed, neither here nor there, neither now nor then, nothing, no time, no space, nothing was there. What happened? Now, quantum mechanics says that this was a quantum vacuum at that time. complete quantum vacuum. And when there are some fluctuations in this vacuum, this vacuum went from a higher energy state to a lower energy state. Okay. And suddenly energy were released. Now, this is the latest concept from quantum field theory, quantum mechanics. Now, and space was also created at the time. Now you see that when in the beginning it was tremendously high temperature, 10 to the power 40, 30 Kelvin. But when it expanded, the entire space expanded slowly, not slowly, but very fast. Cooling effect is there. Expansion gives cooling effect. Now, this cooling effect means that vacuum condensed, condensation of vacuum. Now, you know, when vapor condenses, we get water drops. So when this quantum vacuum condenses, the first particle appear as condensation, Higgs boson. It is called Higgs bosons. I'm not going into details of this. If somebody asks, I can tell. These Higgs bosons are produced first. Then further cooling, quarks and leptons. Quarks, leptons, all these were produced. Okay. 6 quarks, 6 leptons, and their corresponding force-carrying particles, photons, jet particles, all these gluons, these things were produced. So it was Higgs first, Higgs bosons, we call it Higgs particles. Sometimes they call it Gauss particles, that I cannot go into. So ultimately, now we see that in the initial stage, only 17 particles were produced, condensation of vacuum. And these 17 particles later on, through various interactions, produced atom, a proton, neutron, their nucleus, atom, molecule, and matter, everything, and the universe as we see today, including living things, non-living things, whatever is in the universe, ultimately they consist of only 17 fundamental particles. We call them the building blocks of the universe. See the information. What else you need? Quantum mechanics says, what is the ultimate level of the universe at the bottom? So at the bottom, it is only 17 particles, building blocks. Rest is simply just how you combine them, how they form complex molecules through various interactions. That is the mystery of the entire creation. So we now understand the mystery behind creation. That raises a lot of questions now. What is the role of God? But that is a different topic I cannot go into. Thank you all, Dr. Chetri and all that. I have taken a lot of time, I think, and I would like to have some questions if there are.
There are a lot of questions actually.
Select the most interesting one.
Okay, sir. The questions are in the question answer box. It's in the chat box, in my WhatsApp as well. And I have a personal question as well, sir. That will I'll ask at the end.
Please.
Okay, sir. So, Dr. Lachit Saikia has asked, sir, I am curious to know how did Max Planck get the idea of quanta? In other words, what were the driven thoughts to conceptualize the idea of quantization?
You see, have you seen the, when you derive the Planck's law, okay, when Planck derived his law, he first used, that the Bohr's distribution law, e to the power, exponential to the power, minus energy divided by kT. Everybody knows that, Bohr's law, Boltzmann distribution law. Am I correct?
Yes, sir.
So, when you derive the energy of radiation, the classical physics used the fact that this energy appearing there, it is a continuous, it can have any value. So integrated it from 0 to infinity, correct? Because when you integrate over a quantity which is a continuous variable. So they calculated the average energy of radiation, and that came out to be simply kT. kT, you can see classical physics, okay? Now, but Planck attacked this. He said that this energy must be changed. It must take a discrete character, discrete. So he suggested, it is a hypothesis. He said this epsilon, this energy E or epsilon, whatever you call it, is not a continuous variable, but a discrete variable. And he wrote it as epsilon equal to an integer n into h nu, correct? H nu because it has the, h nu has the dimension of energy. He introduced this constant, and this ultimately he introduced a constant, but he did not know what is its value, whether it is a universal constant, correct? So he simply first did trial and error. He put nh nu, okay, nh nu, but h nu he called epsilon zero, the constant value, and then integration was replaced by a summation over n in the calculation, and that made all the difference. Once you replace the integration by the summation, Planck's formula comes out. So Planck said that this is the hypothesis which must be used, that the energy is quantized in terms of a quantum h nu. But value of h, he also determined how, you know. Now you have the formula, okay. Now in formula, say suppose you take an experimental curve, you know the every points at a given temperature, you put the particular temperature there, okay. You know the energy density, the y-axis, okay. So put different values of energy at different temperature and see what value of h you have to put in order to fit one curve. It's a tedious process. And he found out the exact value, what value of h should be there, so that there is exact agreement. Now, once you determine the value of h for one temperature, you see whether it is also true for other temperature. So you consider other family of curves with the same value of h, and ultimately the most interesting point why Planck was so confident is that with the same value of h, he could calculate all these curves beautifully, which agree to the experiment. So this value of h must be a universal constant. That is how we determine.
Okay, sir. So next question is from Ritik. He is asking, in the radiation curves, do temperature correspond color? If they, how we can determine?
No. You see, this what I saw, what I showed this black body spectrum. You know, as I told you, this is simply electromagnetic spectrum. Okay, electromagnetic spectrum contains the visible range also. The visible range is very, narrow, as you see, from red to violet. So that part I have shown you there. So if you take the, you see, you can take the spectrum also. You will get a continuous spectrum like this, right? It is a continuous spectrum. But the invisible part you won't see, infrared, ultraviolet, and corresponding to each range of these wavelengths, you can determine the energy experimentally. There's a technique you can find in any book on physics, how they determine all this energy corresponding to a particular wavelength. So this is how you cannot have all the color. You have all the colors, but not all the wavelengths are observable. But experimentally they can be determined because energy you can determine. Okay, this you allow this radiation to fall, say on some object. There is a measuring device. Okay, and then energy will be indicated. That means there is a frequency there, like that. It's an experimental technique. That is.
Okay, so the next question is from Sirsendu. He is asking, why was the wave function taken as a function of imaginary number? As we all know that real particles should always have a real solution. So why not a real function representing it?
No, it should be otherwise. You see, psi, the wave function psi is a solution of Schrodinger equation. Am I right? Now, Schrodinger equation itself contains the imaginary I. In the equation, IH slash del psi del t. That imaginary I appears there. Am I right? So obviously, the solution psi, mathematically speaking, it will come out to be complex. It will be a complex function of R and T. Only in some, see, this is the most general time-dependent equation that you must know. time dependent equation, most general. But you can also have a time independent Schrodinger equation. That is a different thing. Okay, where it may come out to be real also. Solution may come out to be real, sine function, cosine function. But anyway, I'm not going into, but we must focus on the most general time dependent equation. They are the wave function solution of an equation which contains imaginary I. So in general, psi will be a complex function. We can't help it. Thing is that what is the physical meaning of this? Now, let me tell you, Schrodinger himself tried it, but he failed. Schrodinger initially thought it is a real wave. It represents a real wave, just like water wave or any other electromagnetic wave. But if it is like that, you know, suppose electron has a real wave, then another electron comes with real wave, and real wave is three-dimensional, correct? Real wave is three-dimensional. So it can be shown mathematically that when two electrons collide, right? Two three-dimensional waves collide. After collision, the resultant wave will be six-dimensional. Now, what is the meaning of six-dimensional wave? Can it be real? No. Remember, dimension is a very important concept in physics. Everything real is three-dimensional. If you go beyond three dimension, it is complex. As you know, in relativity, four-dimensional space, x, y, z, and time axis is imaginary. Anything beyond three is. So that is why we cannot interpret psi as a real wave. And it was only by Max Planck that he gave the most relevant interpretation, that psi modulus squared. It gives the probability of finding the particle. Now the question is, where is the wave now? Wave is there. The wave is a mathematical concept here because it is the probability of finding the particle which will behave like a wave. If you plot this probability function, psi modulus square, as a function of R&T, you will see there's a beautiful sine pattern or cosine pattern or some complicated pattern. This is what we mean by wave property of the particle. The particle is not a wave, but the probability of finding the particle in space behaves like a wave. That introduces uncertainty. That introduces indeterminacy. But while in space, when you don't observe a particle, it is simply everywhere, anywhere the particle may be with probabilities. Don't try to look at. But as soon as you try to observe the particle with some instrument, then it will only then it will hit as a particle. That's all. So psi has no meaning as real wave. This should be. And also let me tell you that that's why I told you that you have to study more and more students, especially because these are the, that is why I call it magical, because these are the concepts which trouble any young mind who first come across with quantum mechanics. But thing is that they should know, of course, let them study whatever they want, but ultimately remember, no particle is a wave. In quantum mechanics, we say this world consists of neither wave nor particle. There is nothing like water wave. Do you know? Water wave is a pattern created by complicated motions of water molecules. It is water molecules which are oscillating, vibrating. That gives the picture of a wave. So ultimately, quantum mechanics says that there is nothing like particle or wave. It is a quantum field everywhere. Every particle is a manifestation of a quantum field. You know, when I say electron has a quantum field. We call it electron field. And this field, it is this field that controls the behavior of the electron. So ultimately, we say that the wave character or particle character which you observe experimentally, they come through the quantum field, nothing else. This is the latest idea we have developed.
Okay, so the next question is, do quantum vacuum can explain dark energy?
Oh, no, no, that is a different. See, dark energy, first you must know there is what is dark energy and dark matter. You see, you know that universe is expanding. Okay. Now, in the beginning, this expansion rate, you know, suddenly, you know, that inflationary stage is there, inflationary, tremendous expansion. Now, dark energy, this concept has been introduced just to counterbalance this tremendous expansion so that stability is there. So dark energy is responsible for some repulsive force, you know, it counteracts the attractive gravitational force, correct? Some sort of balancing act. But this is a proposal only. So you can call it the vacuum also, vacuum energy, but it will be negative energy, negative pressure, something like that. Okay, that is also there. These concepts are coming out. But remember, still, it is in a very preliminary stage, concept of dark energy. It is only a proposal that there must be dark energy as a repulsive force, right? Gravitation is an attractive force. And, you know, Einstein, in his equations in general theory of relativity, introduced a constant lambda, it is called lambda. And that he introduced as a repulsive force so that it counterbalanced the attractive force. Anyway, dark energy concept is there. The dark matter is also there. Dark matter, you know, it is assumed to spread throughout the universe. Otherwise, dark matter, we assume that it exists within the galaxies also. Otherwise, so billions of stars in a galaxy cannot remain together. It acts like an additional attractive force. Dark energy acts as an attractive force. But dark matter, it's called dark matter, but dark energy is repulsive. So dark matter, dark energy, they are totally completely different properties and in different context. But dark matter also is not observed as yet, but it is a proposal. But people think that they must exist. They must exist. Only thing is that we are not able to observe them till now. That's all.
Okay, so the next question is from our colleague. He is asking, even though physics students know the equation E is equal to mc square, but to make them accept the fact of particle production from high energy is not an easy task. I would like to hear from explanation from Rajput sir.
No, please repeat it. E equal to mc square.
Yeah, physics students know that equation equal to mc square, but to make them accept the fact of particle production from high energy is not an easy task.
Yes, not easy, not easy. You know, this all this high energy physics, you know, the high energy experiments, GeV and 10 to the power 9 GeV energy, this you all know. Now, why? You see, let me tell you one thing. When you have a mass, a particle is a bundle of energy. For example, suppose proton, take a proton. Within proton, there are 3 quarks. They are bound so strongly, tremendous energy is there. But if you somehow you can break the proton, then what will happen? You get tremendous energy coming out. Just like fission process, you know. Now, so what in high energy physics, what you cannot simply get energy out of mass. So for that, what you suppose you collide 2 elementary particles, protons, collision. Now they are repulsive, so you have to produce a lot of kinetic energy to them, and that is why accelerator and all these things, you know. So if you allow 2 high energy protons to collide, what will happen? They will break, giving rise to new particles with tremendous energy coming out. So you get new particles coming out along with tremendous energy. That is how we get energy out of mass.
Okay, so the next question is from Ipsita. She is asking, is the electron mass strictly of electromagnetic origin?
No, it's not like that. See, origin of mass, I told you about these bosons, these Higgs bosons. Do you remember? Higgs bosons. You know, this is a very interesting question. Concept of mass in physics. Remember when Newton introduced concept of mass? I always say, I used to take higher secondary class also. I used to ask, what do you mean by mass? The elementary definition of mass in textbook is, mass is the content of matter, content in a body. Then I ask, what is matter? It's a matter which occupies space. What is space? He doesn't know. There is no definition of mass. Right? That is why these laws of motion called laws of inertia. First law. Mass is a measure of inertia. Now tell me what is inertia, that you have to find it out. More mass means more inertia. Less mass means. So inertia, you know. For example, you are 60 kg. A baby cannot lift you up. You have lot of rest of inertia. Inertia of rest. So it's like that. Light thing. Okay. Now the quantum mechanics has an answer. Mass of all these elementary particles, like electron or whatever, it comes through Higgs bosons. In the beginning of the universe, you see, you can say there's a standard model of particles. I told you, according to standard model of particles, elementary particles should have no mass. All particles should have mass, should have zero mass, massless particles. This was a big challenge for the theory. That is why Higgs and two more people proposed that there is some particle like Higgs boson. They proposed theoretically, and this Higgs boson can interact with these particles and give them mass through interactions, energy. They can give energy, and they acquire mass. And that is why in the beginning Higgs bosons were produced, and when these massless particles were there, they had interactions with bosons. Yes, the Higgs bosons. I cannot go into the details. It's a lot of mathematics is there. Now, so how many Higgs particles, there are Higgs particles also, interact with a particle, another particle, that will correspond to the amount of mass it will have. So different masses of particles that we observe today, it happened long back in the beginning. They acquired from interaction with Higgs bosons. So Higgs bosons give mass to elementary particles, but still you do not know what is mass.
Yes, you can say that.
Talk about mass.
Amar sir, what is it something?
Yes, yes. You can say that Higgs will provide the required inertia to be massive particle. That Higgs field can provide the inertia for a particle to become massive. You can explain like this. And one point in EPR experiment, you explained the experiment, but you did not mention the EPR experiment, that famous experiment, Einstein, Podolsky, and Rosen experiment.
Okay, that is a different situation. EPR.
That is another issue related to inflation. That inflation area is mass more interesting than the Big Bang.
No, it's not clear. I don't hear you. What is that?
That inflationary universe. That Alan Good.
Inflationary stage.
Yes, this stage is much more interesting than the after some time of the Big Bang.
No, you see, you know that the Big Bang theory, it is the first theory proposed, but later on many modifications were there. And the inflationary model was, Alan Guth, that he proposed this. This was necessary to explain some of the experimental observations of the universe. The tremendous explosions were there, expansion was there within the 10⁻32 second. That is the original size expanded up to 10 to the power 20 times, something like that. It's a very large expansion.
10
And
to the
within
power
that,
50 in a second.
yeah,
10 to the power 50.
yeah, like that. Order I don't exactly remember within that order. So it was tremendous expansion, inflation that should be there. Otherwise, we cannot have this universe as we see it today. There are certain effects, horizontal problem, and all these things cannot be explained otherwise. This is the idea.
Okay, so the next question is a little bit interesting. The Gyanjyoti is asking, sir, please explain briefly about the most popular quotation of Einstein, God does not play dice. So why Einstein quoted this line? He want to hear from you.
Okay, that's very interesting. You see, when this it was known that quantum mechanics said everything is indeterminate, indeterminism, nothing can be known exactly. Einstein was not happy. Einstein said that you must know exactly everything. Otherwise, what is the utility of physics or science? If there is always some indeterminacy, probability, what is this nonsense? Okay? That is why he said, God does not play dice. Dice, gamble. God is not a gambler. See, when you play dice, you do not know the result. So he was that. Physics or science, see, God, after all, determines everything. So what do you say? So God does not play dice. This was his reaction. Then later on, Stephen Hawking, even other physicists also, this is a very famous sentence. Stephen Hawking, all of you know, he reacted. He said that Stephen Hawking said that God not only plays dice, but he sometimes confuses us by throwing them where they cannot be seen. So God plays dice. Now let me tell you one thing here. There's an interesting situation going on. What is God? When physicists used to discuss. John Wheeler, Professor John Wheeler, he was the supervisor of Professor R.P. Findman. He once commented that if you talk about God, you must introduce two gods. One is classical God, another is quantum God. Now, classical God runs the classical universe. Everything is definite. Everything is disciplined. No rules are violated. No quantum tunneling. No quantum entanglement. No uncertainty. Everything is fine. Everything is fixed. But now we see there is another world, another universe, quantum world. Everything is uncertain. It is quantum God. Now then he said, what is this? Quantum God is like a drunk man. Drunk God. Classical God is a pure, ideal. Now, since God is drunk, jokingly, so what happens? What happens to a drunk man? Suppose he drinks a lot, wants to come to his house, home. Can he come straight? Sometimes he'll fall down somewhere. He may fall in the drains also, enter somebody's house. But ultimately, he can make it. So his trajectory is not defined. Trajectory of a drunk man cannot be defined. That is something. So that is the interesting point. Anyway, these are again another topic.
Okay, sir. Two of the people want to hear about quantum teleportation and quantum entanglement.
I just told you briefly. See, that I told you that quantum entanglement follows from a very important concept of quantum mechanics. This is called quantum correlation. Quantum correlation or entanglement. That is when you produce a pair of particles, identical particles, say 2 photons or 2 electrons, they are produced with a definite values of spins, correct? In case of photons, they are polarization. In case of electrons, spins. Now, when at the birth they have definite spins, this will continue to be so, continue to remain so for all the time. It's eternal. So even if you separate this pair of particles, what will happen? Their spins are well defined. One is up. If one is up, the other is down. Now, this means that whatever be the separation, this information will be contained. You cannot disturb it. But suppose one of the electron is disturbed by some external agent, disturbed, then his spin orientation will be disturbed. And the other electron, which you do not know where it is, or you do not disturb it, still it feels the disturbance, and the spin will be accordingly oriented. So this means as if you can send a message from one electron to another electron without any media, without any medium. This is called quantum entanglement, and this is what is called quantum teleportation. But remember that teleportation means not physically, because physical signal cannot travel at a speed higher than the speed of light. But this disturbance can be at a speed greater than the speed of light. It is called violation of causality here, and it is true experimentally. So this is the teleportation and concept, and on this basis they are trying to build up this quantum computation and computer and all that. But details they can find in any article.
Okay, sir, we're still having so many questions, so we'll not go to too many questions. I will ask my personal questions. I am just taking
sure,
this
please,
leverage of being the coordinator. So why are we still in progress in superconductivity? Means, have we entered the era where we are doing just permutation and combination of different materials? Are we moving blindly in this field?
No. Nothing is blind in physics. See, let me tell you one thing. Superconductivity was experimentally discovered in 1911, I think. Okay. Kamerlingh Owens, when he was measuring the resistance of mercury. Okay. Suddenly at low temperature, the resistance goes to zero, exactly zero. But this was discovered in 1911. But till 1953, there was no theory. Quantum mechanics was not, even quantum mechanics, nobody could, understand using quantum mechanics even how to explain this superconductivity. Then in 1953, Bardeen, Cooper, and Schrieffer, they used, I just called method of second quantization. Method of second quantization to develop a theory of superconductivity. But before using the method of second quantization, Cooper, one of the collaborators, he proposed the most important concept behind this theory. It is called Cooper pairs. Okay, this Cooper pair, as you know, it's a pair of 2 electrons, and 2 electrons can bind together. Now you might think how it's repulsive. This is the beauty. But they would opposite spins. It is the binding occurs through the exchange of phonons that you said. Now that is superconductivity. Already the theory was available in 1953. Now we have high temperature superconductivity. Around 1983, that high temperature superconductivity was discovered in Germany for the first time, and lot of compounds, elements, complex molecules, everything. All this, lot of substances are there which can show superconductivity under certain conditions. Now the thing is that experimentally we observed them, but still we don't have a very convincing theory for this. There are many theories developed, different ideas, but still there is only partial success. It's a very, very highly complicated problem. Let me tell you one thing again. This, apart from this, there is another very complex problem in physics, which I happen to do, publish a few papers. That is, there are certain substances which behave as a superconductor as well as ferromagnetic over a small range of temperature. Now, you know, ferromagnetism and superconductivity cannot exist together, because a superconductivity electrons spin must be antiparallel. In ferromagnetism, electron spins must be parallel. So how these two opposing behavior can exist together? But you can develop a theory. It is a very difficult using Kondo Hamiltonian method of second quantization. One of my students did work on this. It's a very, very interesting problem. And we developed the entire mathematics, which using a lot of calculations are there, method of second quantization. Ultimately, we could find some graphs and all that. And then we show that there is a two phases, and there is an interaction of the two phases, superconducting phase and magnetism, ferromagnetic. There's a small region where both can exist together. And that has agreed with the experimental results. So still theory, but this maybe, this we have done only for a particular example, particular material. But maybe this may not work in some other material, you know. So this is the problem. So still we don't have a unique single theory.
Exactly. That's why, sir, we are just moving around the materials. We try this, we try that combination.
Only ad hoc theories, ad hoc theories.
Yes, sir.
Not a,
Sir, there are many people. So there are many people who are saying that it feels like they have entered the late 90 period when you used to lecture through the lectures in classroom, and they were used to be students. They are very happy about that.
What is that?
Means many your ex-students are putting comment in the chat box that it feels like they are in their late 90s, 98, 2000, when they used to be a student and you used to be their teacher and throwing the same type of classes in their classroom.
So I'm glad to know. Okay.
And they are very happy about that, sir.
I'm also
and they
happy.
are thanking you for delivering such a great speech, sir. Such a great talk we had. We just go through the eras, starting from the 1900 to 2000. We talk about superconductivity as well at the end. So beautiful, sir. Just no word to explain how it was so convincing when you talk. It feels like we are just seeing the electrons, the quartz particle. It's just like a different thing, sir. And after
thank you so much, sir.
In these periods, when people are thinking only about the sanitizers, at least we had a 2-hour discussion where we talk about charge, particle, quantum mechanics, particle, antiparticle, and all these things. And this is very pleasing, sir. We are very happy.
Dr. Chetri, let me tell you.
Yes, sir.
That, that's why those who are really want to understand physics seriously, you know, physics is as my feeling, physics is the only subject which never stops interesting you, exciting you.
Exactly.
It is a subject of excitement, you know, all the time, all the time. More you read, more excited you become. Exactly. What else you need in life? Tell me. Life, if there is no excitement, it is lifeless.
There is no life, sir. Exactly.
Huh?
There is no life.
You know, Professor Paul Davies, one of the famous theoretical physicists, he made a profound sentence. If you want to learn how God thinks, what is God? Don't go to any religious places, religious temples. Don't read any religious books. Come to physics. Study it seriously. And it will lead you to the mind of God. How God thinks, how God works. And knowing the mind of God is more important than looking at God. You may know somebody, but you may not understand him or her. Understanding is more important than knowing. Physics gives you this. And famous, there are many quotes I'll give you now. You see, Einstein, when he was asked such questions, he said that once, the most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. Mysterious, which has no mystery, and those who do not try to understand mystery, they are useless. Okay, thank you so much, Chetri.
Yes, sir. Thank you very much, sir. We'll take another 5 minutes of yours, sir. I know you have a busy schedule. We have some formality to do.
Please carry on.
Okay. There's some announcement for the participants. As I'm talking to you, I have just dropped this feedback link in the chat box. Just fill it up before 8 p.m. tonight, and you will have your e-certificate in your mail or in the WhatsApp group by 9 p.m. tonight. So just fill up this feedback link before 8 p.m. tonight, and you will have your certificates by 9 p.m. Okay. Now, sir, we'll move to the vote of thanks. I'll request Dr. Mathuranath Bora of our Department of Physics, DR College, to deliver his vote of thanks. Mathura, sir, it's up to you. Yeah, please unmute.
Sir, on behalf of the organizing committee, I would like to convey my deep sense of gratitude to our respected Professor Amarendra Rajput, sir. Actually, sir is delivering the talk, very tough talk, but in a very simple and interesting way. All are enjoying the talk, I think, and I become nostalgic, sir, because I feel like in MSc with our loving sir. Okay, I would like to express my thankfulness to sir. I would like to express our thankfulness to our respected principal sir for his guidance. We are also thankful to IQSC, DR College, namely coordinator Zinku Bogotoki and Biplab Gogoi. We'd like to appreciate all the helps offered by the technical committee, and at last but not the least, I would like to express my thankfulness to all of our participants, and I also request Dr. Pawan Chetri to upload this most valuable and most interesting talk in YouTube. Then all will be helpful, all will be benefited. Sir, thank you again, sir. And now I over it to Dr. Pawan Chetri.
Thank you, Mathura. Thank you so much.
Sir, it's just a small question. Some people are asking, can you, sir, name a good book for mathematics students or researchers who wants to work on quantum mechanics?
Any good book?
Yes, sir. For a beginner, people from mathematics background to start doing research in quantum mechanics.
Dr. Chetri, let me tell you one thing. It's very difficult to mention one book or two books like that. It's very, very, you know, as a student of physics.
Exactly.
Now, let me tell you, in our time, but this time is totally different. In our time, there were no books as such. Nowadays, market is flooded with books. Indian writers, foreign writers, whatever, you know, that's all this. Now, when in our time, we had only one book by Schiff, L.I. Schiff, okay, but that was not sufficient. Now, when I became a teacher, of course, in MSc and all that, we depend on the lectures and all that, what the teacher said. When I was assigned taking quantum mechanics class for the first time in Libreville University, I was at a loss because a as a student and taking exam is different from teaching a student in the class. To teach a student, you must know first everything. Then you can carry this to the student. So I remember still at the time from the library, I went to the library and extensively I studied books by all the famous authors. I mean, all these brilliant authors. But most of those books are not available nowadays. That is the problem. And remember, no Indian books were available at that time. But today, of course, there are many books, including by authors. And but most of them, I've seen that they are just simply examination oriented, most of them. It doesn't give the real knowledge. So it depends on whether you want to know quantum mechanics or you want to do well in quantum mechanics in the examination. That way you have to find. Now, if somebody really wants to know quantum mechanics, and also, say, if you know, you can easily do well also in the exam, but not the other way. So what I have seen that there are books. One classic books are there by Dirac himself, Principles of Quantum Mechanics. That is a bit tough. Huh? Principles of Quantum Mechanics. His language is a bit different. Then now I have also saw two books, Advanced Quantum Mechanics and Quantum Mechanics by F. Schwabl, F.SCHWABL, F. Schwabl. There are 2 volumes. It's quite good. And if it is available, A.S. Davidov, A.S. Davidov, D-A-V-Y-D-O-V. It's a very good Russian author, but I do not know whether it is available. I wanted to procure it in the library here, but it was not available. Then there are also books by Landau and Lifshitz. Relativistic quantum and non-relativistic, very well written, but you have to be a bit, you have to apply your mind. But once you understand this concept, coming to Indian authors, I have found one that very good book by Kotak and Lokonathan. That's a very good book I have seen. Kotak and Lokonathan, Quantum Mechanics. It's a very good book. And there are also one book by Matthews. That is also good book. Small book, but good book, Matthews. So there are many, but Indian, usually I am not very familiar with these Indian books. But still, thing is that it is the reader, that student or a teacher who can find it out. Because a particular book might suit you and you may be liking it. Read it, you'll learn it.
Exactly. So thank you very much, sir, for accepting our invitation for this lecture. You just accepted on a one call. We are very glad for that. And I was an unknown quantity to you, but you just received my call and you just agreed to give a lecture on this topic and giving us so much time. And we had a very good, pleasant time last 2 hours. We are very thankful. And we are hopeful that once this pandemic will go, we'll have you physically in our college for the whole day, sir.
Let us see. Let us hope for this.
And thanks to this network connectivity that we have been able to hear you so smoothly. There was no single interruption. So thanks to the network, whatever we are using, thanks to the network, thanks to technology.
It's a quantum effect, It's a quantum effect.
Exactly, it's quantum effect. So thanks to everything. And thank you once again, sir, for coming and giving this lecture.
Oh, it's my pleasure. Very good pleasure to interact with all of you. Okay, thank you.
And I am very much sorry to participants. I could not ask all the questions of yours because there was too many. But hopefully, sir have answered all the questions. And sir has suggested some book as well. Go through the books. And it's all about reading the books and imagining the things with a proper knowledge. Okay. Thank you, sir. Thank you all the panelists. Thank you, participant. And sir, I'll talk to you later, sir.
Okay, sure, sure.
Thank you, participants.
Okay.
Okay, sir. Do fill up the feedback link before 8 p.m. Thank you.
Okay.
Thank you, sir.
Okay.